Hello friends, this video on application of derivatives part 8 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 7. Let's take one theorem. And before we take this theorem, let me tell you why are we taking this theorem. The reason why we are taking this theorem is the current approach to find whether the function is increasing or decreasing is we have to first find f of x1. Then we have to find f of x2, correct? And then it may be true that the point which we have selected for this is true, but this may not be true for all the points x and x2, correct? So in that case, I'll show you an example. For example, if you take this graph, correct? And my graph is like this, correct? This goes down actually also like this. Let me draw once again. My graph is like this. If I take my point x1 this and x2 as this guy, correct? So with the formula, I know that this guy is greater than this guy is greater than this guy. So with my current formula, I'll be able to prove that. See, with the current formula, I can see that x2 is greater than x1, correct? And f of x2 is also greater than x1. Why? This guy is f of x2, this guy is f of x1. So this guy is greater, f of x2 is greater than f of x1. This is true. x2 is greater than x1. This is true. But we know that this guy is not increasing. Correct? So logically what we have to do is we can't tell the function is increasing or decreasing just based on 2 points. We have to keep on finding other points also, whether, correct? So this is the problem, because if you take a long difference between x1 and x2, you may find a solution which says that this function is increasing or decreasing, but actually it is not increasing or decreasing. To avoid such kind of thing, we have a new formula that says that if f is a continuous function on a and b and differentiable on the open interval a and b, then f is increasing in this interval if f dash x is greater than 0 for each x that is member of a comma b. Also, f dash is a decreasing function if f dash x is less than 0 for each member of x member of a comma b. For each, please note, for each, here also for each is there, because for each and every value of x here I have to prove that. Also, f is a constant function if f dash x is 0 for each value of x and b. So with this, I need not find the value of f of x1, f of x2 everywhere. I can just find the value of f dash x, correct? And these x I have to find for all in this range. So this is a theorem which makes our life simple to find whether the function is increasing or decreasing function. The early example, we used to find f of x1, f of x2, and still there were loopholes there, correct? Because we had to find all x1, x2. Here we just have one value x, and for example this is x. Now at this x, I want to know whether the function is increasing or decreasing. I can find using this, because this formula is independent of x1 and x2. At that particular point, we can find where the function is increasing or decreasing. The earlier formula we had 2 inputs, x1 and x2, and sometimes the results were dicey also. Now with this, I have only 1 point. I have to tell whether at this point the function is increasing or decreasing. So with the formula, you don't have to do anything. You have to just differentiate the function. You find f dash x, correct? So if you have this function, you have to find f dash x. Now if this is less than 0, it is greater than 0, 2 options. It is greater than 0, it is increasing. It is less than 0, it is decreasing. Now you may be wondering how I got this formula. So let's take the proof of this theorem. To prove this theorem, we'll use the same logic that if x1 is less than x2, any numbers in the domain, and if my f of x2 is greater than f of x1, then my function is increasing function, and if for increasing function, and if my f of x1 is greater than f of x2, then my function is decreasing function. The same logic we'll use. So let's assume, let x1 and x2 be two values in a comma b, because I have my function f of x whose domain is a comma b. Now if I want to find f dash c or f dash at any point, let's suppose I have to find f dash, this is nothing but f of x2 minus f of x1 by x2 minus x1. Correct? Where c is a number between x1 and x2. If you see how I have done this, if this is my graph, correct? If my x1 is this guy and x2 is this guy, if I want to find a slope at this point, let's suppose c, so this is nothing but slope, we know that is slope. And this guy, when I say f2 fx2 minus fx1, that is nothing but y2 minus y1, because this guy, if you take this point is nothing but x2 comma f of x2, correct? And this point is nothing but, I write here, x1 comma f of x1, correct? So this is nothing but y2 minus y1 by x2 minus x1, because this guy is slope. So slope at this of this line is nothing but f dash c, and that is nothing but y2 minus y1 by x2 minus x1. y2 and y1 is nothing but f of x2 and f of x1. So this is what I get. Now if this guy is positive, case 1, this guy is positive. If this guy is positive, see x2 minus x1 is always positive, correct? Because x2 is greater than x1. This guy is always positive, always positive. If this guy is positive, f dash c is positive. So case 1, f dash c is greater than 0. In that case, f of x2 minus or f of x2 is greater than f of x1. Correct? Why? Because f of x2 minus f of x1 has to be greater than 0, or this implies f of x2 is greater than f of x1. In case 2, when I say that f dash c is less than 0, since this is positive, this has to be less than 0. So in that case, this minus f of x1 is less than 0. Or I can say that f of x2 is less than f of x1. So this implies, if you see, this implies this guy is same as this. That means function is decreasing. And here, this is nothing but this guy. This implies function is increasing. Correct? So if f dash c is greater than 0, function is increasing. If f dash c is less than 0, function is decreasing. Case 3. Mine was f dash c is equal to 0. If that is the case, since the denominator is always 0, always positive, in that case f of x2 minus f of x1 has to be equal to 0. In that case, f of x2 is equal to f of x1. If that is true, that means function is constant, like this. You take any value, x2, x1, this guy is same. This guy is f of x2, this guy is f of x1. This guy is x1, and this guy is x2. Correct? So what we have done, we have proved this theorem, and theorem says if f dash c is greater than 0, the function is increasing at that point c. If f dash c is less than 0, the function is decreasing at that point c. If f dash c is equal to 0, the function is constant at that point. We'll take some examples of increasing and decreasing function. So we have to prove that fx 3x plus 17 is strictly increasing on R. So we have done similar kind of question where we have taken 2 points, x2 and x1, and then we have found x2 and f of x2 and f of x1, and we showed that f of x2 was greater than f of x1 for x2 is greater than x1, right? So we have done this kind of question where we have taken x2 is greater than x1, and we have proved that f of x2 is always greater than f of x1. Now we'll do with the easier way. The easier way says that if f dash of x is greater than 0 for each x that is part of this domain, that is real number, then I can say that it's always greater. It's not greater, it is greater. If f dash x is greater than 0 for each x, then I can say that the function is strictly increasing. Using theorem, so let's find f dash x. So if my f of x is 3x plus 17, my f dash x will be nothing but 3. And this guy is always greater than 0. You take any value of x, it is greater than 0. Why? It is independent of term x part. So this guy is greater than 0 for any x that is number. So I can say that this function is strictly increasing. Why strictly? Because it is greater than 0. It is not greater than equal to. It is greater than 0. Correct? Let's take one more example. Again we have this function e to the power 2x. We have to prove that this is strictly increasing on R. Same thing, we have to prove that f dash x is always greater than 0 for each x that is member of this domain, that is R. Please note, for each x. So let's find f dash x. F dash x will be nothing but e to the power 2x into 2. Now we know that e to the power something is always greater than 0. It's always positive. And positive into positive is always positive. So this guy is always greater than 0 for any x that is member of R. You take any value of x, you take even if you take negative value of x, this guy is positive. E to the power x is greater than, let's suppose, minus 5. Minus 5 into 2 is minus 10. So e to the power minus 10 is also positive. You take any value of x, this guy is positive. So this is strictly an increasing function. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.